Hello, in this video we'll talk about total internal reflection and critical angle. Total internal reflection and critical angle. This is a very important concept in geometrical optics. A lot of questions are going to come where we are going to use this concept. So please pay attention. As we said earlier, if we have two mediums, this is medium 1, this is medium 2, it has a refractive index N1 and it has a refractive index N2, and N2 is greater than N1, so this is a lighter medium like air, and this is a denser medium. And light goes from lighter to the denser medium like this. What we observe here is that when a light is traveling like this, some of it will get reflected and some of it will get refracted. And we wrote a simple formula to understand how the energy will behave. This is a total energy E coming in. This is which is going to be reflected, and this is energy getting refracted. And we say to hold the energy conservation, total energy will be always equal to energy reflected plus energy refracted. Now, how much will pass through or get reflected and how much will bounce back or get reflected really depends upon the angle of incidence. So this is the angle of incidence I, and when we sort of put the ray of light right like this, so the angle of incidence is 0. We can see that about 4.5%, 4.7% of the energy is getting reflected back and rest of it is passing through. Now when we increase that angle of incidence to, let's say, 60 degrees, we can see that about 9.8% or about 10% is getting reflected back and 90% is passing through. And when we further increase the angle to, let's say, all the way to 90 degrees, the ray of light is now coming parallel like this. So the ray of light is now coming parallel like this, and with Snell's law we observe that there's no refraction basically, and all the energy will get reflected back at 90. So the 100% of the energy is getting reflected. Now this is true for all the medium when the light is traveling from a lighter medium to a denser medium. Okay, so the light is traveling from a lighter medium to a denser medium. We can always use Snell's law here to find out the angles of incidence and angle of refraction, and angle of reflection will be equal to angle of incidence. Now a new phenomena will occur when the light will go in the other direction from a denser to a lighter medium. So let's study that. But before we go to that, let's write down the law or concept. When we say when a ray of light propagates from lighter to a denser medium, we observe that reflection as well as refraction, the energy which passes through the medium or via refraction decreases as we increase the angle of incidence. So in here we are observing reflection as well as refraction, and as we increase the angle of incidence from 0 to 90 degrees, this value decreases from 95 to 0. So this is decreasing and this is increasing, and that's what we want to remember. We have written as concept. Now let's change the setup, whereas we have light now going from a denser medium to a lighter medium. So we are going to write it here. This is glass, so this is a denser medium, this is lighter medium, and now instead of coming like this, the light ray is originating from this source and going in this direction. So as if the light ray falls perpendicular or when the angle of incidence is 0, we can see that there is no refraction and sorry, the angle of refraction will be 0. We can find that with the Snell's law, and about 5% of the energy will get reflected. So very less is reflecting and about 90%, 95% is going up. Now if we increase that angle of incident to, let's say, 30 degrees. So let's say this is our 30 degrees, right? So we first draw the normal here. Now we have our reflection. So this angle and this angle, both I, and this is our angle of refraction, which we can find via Snell's law, by writing Snell's law equation at this point, which is n is equal to 1. So that is, we know that n is equal to 1 for air. So 1 into sine r will be, let's say the refractive index of glass is n, so n here of glass, or ng, into sine I, right? And we can always find that r, and we found that this is about 51 degrees, and we know that the light is traveling from denser to lighter. It is going to be deviated away from the normal, so the angle will increase. Now we can see that about 6.8% of the energy is getting reflected back, very less. And as we'll keep on increasing the angle of incidence, we'll see different phenomena. So let's clear the board first. So we can see that basically this angle is now sort of increasing here, right? So this angle is increasing as we go along, and on around 40 degrees, when we have angle of incidence is 40 degrees, so this is our normal, and the angle of incidence is about 40 degrees. So let's say this is our normal, and this is the angle of incidence is about 40 degrees. We see that the ray of light behaves differently, right? So the ray of light will come like this. Part of it will get reflected back. So this angle will be also 40 degrees. By using Snell's law, we can find that the angle of refraction now is going to be 90 degrees. This angle is 90 degrees, so that all the light is actually getting reflected back and none is passing through. Hence, we can see that now the 100% of the energy is getting reflected back and none is passing through. So all the light beyond this 40 degree angle, when we increase it further to, let's say, 50 degrees, here all the light will get reflected back, and this phenomena is called total internal reflection. Okay, when all the light is getting reflected and nothing passes through or nothing is reflected, this happens at a very critical angle when the angle of refraction becomes 90 degree. So we can write the equation here. So this is the refractive index of air, let's say, and this is the refractive index of glass. We can write the Snell's law at this point, where we say n of air into sine of 90 will be equal to n of glass into sine 40, right? Or in general case, we can write n of glass into sine angle of incidence I. N of air is considered 1, sine of 90 is also 1. So we have this equation like this, where we can say the refractive index of the medium from which the light is traveling, which is n of glass, into sine of I, critical angle when this phenomena is observed, sine CR, is going to be equal to 1, or when sine I critical has to be greater than 1 by n, we'll observe this phenomena, right? So for the light to get reflected back and no refraction to happen, this angle has to be more than 40 degrees. So here we have 40 degrees. In the next ray which is coming here. So this is the 40 degrees, and now this one is coming like this, and we can see that this angle here is more than 40. So for all the angles which is more than 40, no light will pass through, all will get reflected back. Okay, and that critical angle we can find by a very simple equation which we have already written here, is IC will be sine inverse of 1 by n, which is this equation. Okay, now recapping, we want to know what are the conditions for total internal reflection, and we are going to write it down as an important concept. So first condition is the light has to travel from a denser medium to a lighter medium. Second condition is the angle of incidence has to be greater than the critical angle for critical angle. This critical angle can be calculated for the pair of mediums. So we can calculate that by equating the sine I to be is equal to 1, and this has to be calculated. Now so when we are considering that the other medium, the lighter medium is air, we can simply calculate those. And here we have, so for carbon disulfide we have 38 degrees Celsius, 38 degrees, water about 49, glass light crown 40, 34, like that, right? So we can already calculate these critical angles for different set of conditions where when the light is sort of going from a denser medium to lighter medium, or in this case air, where the other part is I. But if for a very general case we can write, so for example we can write something like this. So we have let's side right. So we have this medium, sorry, interface here, yeah, and here we have medium N2, here we have medium N1, and N2 has to be greater than N1, so the light will travel from denser to a lighter medium. And now when the light will come like this at a particular angle I, and it will get reflected totally like this, so that this one is 90 degrees, we can write N1 sine 90 will be equal to N2 sine I. For this to happen, we'll say it's the critical angle, so we can say this one is sine IC will be equal to N1 by N2, or for total internal reflection to happen, sine IC has to be greater than N1 by N2. Okay, so this is the equation we will derive and can remember. So there are a lot of applications of total internal reflection. As we can see here, we have a prism like this. The light is coming, getting totally internally reflected, and hence the direction of light changes by 90 degrees. We have another prism here of different kind. Light is coming like this, and reflection is happening over here. So the ray of light bends, but getting totally internally reflected here, then comes here and reflection happens, and we have a parallel but a shifted beam, right? Now here is a optical pipe we can build. So light is coming here, it is getting totally internally reflected here, 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 and finally coming out. So without any loss of energy, all the light can move from here to here, 100% totally internally reflected. So there is no loss of energy, and these kind of things are very useful in optics for transmitting energy from one place to another. We can in fact transmit some picture here, which will come out here like this. Even if we have a bend, the design could be such that the light is getting totally internally reflected, and this is the concept for the optical fiber. Without any loss of energy, we can transport light from one place to another, or a message from one place to another. And here in the prism, we can sort of change the direction of light without any loss of energy, because here the total internal reflection is happening and all the energy is going through. So this concept is very important, and we will, in the next video, we'll look at a couple of problems where we are going to use this concept. And please bear in mind, this is so important that every time a question is going to come, to check about this concept. So I advise that you actually completely understand the concept and practice a lot of problems using this concept before exams.